Time-independent approximations. There are two different important topics. One is perturbation theory, we will discuss today. The other is variational method. Both are discussed in the end of quantum physics class, which is usually discussed over 1 year. So we will simply take the solutions for perturbation theory, then discuss the application examples. Here just the same variational method will be introduced, and then we'll discuss the examples. Previously we discussed 1 plus 1/2 system. This is another important quantum physics problem, and we will see these issues many times in noble materials. So these are actually important problems. So total angular momentum quantum number we considered, and its g-directional values we considered, and the correlation between the new state JJG and original independent state consisting of LG, SG. Those are correlated by classic Golden coefficient. Here classic Golden coefficient is 1. Classic Golden coefficient is here, and here, and here, and here. Here plus minus, which matches with minus plus sign, plus minus matches with plus minus sign. Okay, this slide is the last one for this class. I know it has been very hard. I think it is one of the most important, well, it's maybe most difficult classes now. I'm pretty sure if you study the hardwares, then it will be useful in the end. At least for me, I could write down many papers, research papers based on these studies. By the way, final exam will be notified pretty soon, and it should be around like 3rd week, I think. Of this month. By the way, the number here is the items to indicate the different topics, but we skip some of the items this semester, so please understand that. Just have chosen, we all have chosen something more important than others. Otherwise, we cannot, suppress all the topics within one semester. Especially this semester, I even had this surgery, so I'm somehow sorry for any inconvenience and any complications. I'm sure you will get to know the importance of these classes. So, once you introduction to approximations, one is papers, perturbation. Okay, the other is variational method. Both are extremely important. So most of your simulation tools for semiconductor devices are actually depending on perturbation theories or variational methods. We already studied the WKB method, so we'll skip this part. We studied this for tunneling, right? Tunneling will be another issue for final exam. So basic idea is quantum physics problem, quantum mechanics problem is very hard to solve. So we want to make it simple. Even the hydrogen atom, which is solvable, it was actually pretty complicated, and there are way more complicated problems in quantum physics. It cannot be solved analytically, so we need to develop methods that can be employed to approximately solve difficult quantum problems. So we want to make it simple. So basic idea is total Hamiltonian is very complicated. Then we separate them into two parts. Simple part, which is easy to solve, and correction part, which is difficult, H prime. Originally, we need to solve both of them at the same time, but this correction part, it is considered to be small. So that's the main idea. We somehow reduce the importance of this correction part in a perturbation method. Simple part we solve, and it is used as a starting point for approximate solutions. Variation method we will discuss next class. Yeah, well, I'm repeating the same ideas here, but in more detailed scientific terms. Okay? Does it matter that much? Yeah, it matters actually. In terms of research, you will repeatedly see some of these terms. Okay? And there are even some examples. Stock effect or quantum confined stock effect, those are very important. And this explains the exciton energy. Exciton, we discussed several times, it is electron hole pair, and it is slightly below the band gap energy. And exciton is the key parameter to determine the optoelectronic device functionalities. Well, sometimes, yeah, computation is useful, so we have many simulation softwares instead of mathematical approaches. Please read through yourself. I'll skip this part. This can be found in any textbooks. This is just another explanation. Just the same with the previous slide. So basic idea is here. Let's say we have this Schrödinger equation, H Hamiltonian operator, so H psi. Psi the wave function, then energy wave function. Then this H is split into two parts. H0, which is simple, H prime is difficult. So can we solve this Schrödinger equation with new Hamiltonian? Usually it is very hard. So H0 will be solved like this. H0 psi n0, simple part. Then we have En0 and psi n0. Let's say solutions are known. Then perturbation part H prime. Let's say it is rather small. Okay. Then what we are doing is, it is supposed to be H0 plus H prime. H prime is the key issue here. Too difficult. So instead of H0 H prime, we rather set it like that. Lambda set to be small. Lambda is supposed to be 1 to solve this, but we intentionally set lambda, which is to be smaller than 1. Okay, so let's make it smaller than reality, than real h prime, then what we are doing is we put this into here. Sorry, put into here. Put into here. So, and then h is set, but psi n, en is designed like this. So we add them into here, psi energy. So let's say there is certain quantum number. So we add them like this. Psi and zeroth order, first order, and so on. And then this is the same with energy, zeroth order, energy, first order, and so on. And the wave function again, same wave function. And here, if we set lambda is very small, then we can ignore the higher order, right? Yeah, so basic idea is we compare both sides in terms of the order of lambda. So first order will be arranged and then we solve the equation. Second order will be arranged, we solve the equation. Third order we arrange both sides and solve the equation. Yeah, that's it. So yeah, it is explained again. So same ideas, but more detailed explanation, but it's just the same. Yeah, what we are doing is this. Okay, and then this equation is valid between the same powers of lambda, because we didn't set lambda yet. This is arbitrary number smaller than 1. It is supposed to be 1, but if it is 1, then way too hard to solve. So it is impossible to solve the case for lambda equal to 1. So we set it intentionally to be smaller than 1. So let's say lambda is not determined yet, it's arbitrary. And then the different orders are arranged here, unperturbed, Hamiltonian. So zeroth order, no lambda dependence. No lambda dependence. Here you compare both sides. Then you see the H0, psi 0, low lambda dependence here. On the right hand side, E0, psi 0. That's the zeroth order. Likewise, first order you can consider this one multiplied by this one, right? And this one multiplied by this one. First order. On the right hand side, this one multiplied by this one. And what else? This one multiplied by this one. Then you have first order. Then you compare both sides. Then you have this one. Okay? Yeah, you can arrange those in terms of zeroth order and first order wave function. So if we know the zeroth order wave function, then you plug it into here, then you calculate this one. Okay, so if zeroth order is determined, first order is determined. Yeah, likewise for the second order lambda square, you compare both sides again. So in this case, second order you have here, here, you have here, and here, right? On the right hand side, you have this one multiplied together, and this one, and this one, and this one, right? Then you have this equation. Again, this will be arranged in terms of the order of wave function. So second order, wave function can be arranged in terms of first order and zeroth order. So zeroth order was calculated here. You plug it into here. First order you calculate here, then you plug it here. So you go higher and higher. Now 2, 3. Third order term, fourth order term, infinitely added up. So yeah, it takes time, but if we make some simulation software, then it can automatically determine. But if you set like a lambda equal to like 0.5, for example, let's say lambda is intentionally set to be like that instead of 1. 1 is way too hard, so we will set this like this. But then lambda square 0.25. It's already like a 25%. So and then lambda to the 3, like almost 0.1. 10%. So we ignore this part. So you will have 10% of error in the solution that way if we ignore the higher order from the third order terms. In the software, you can go to the higher order, but in analytic ways, it's way too hard. So we will just ignore, for example, the third order. Let's consider the energy is good enough with certain error. There should be errors now. But let's ignore the higher order term. Okay. So the energy is determined like that to the second order. So first order solution is calculated like that. We didn't go into the detailed mathematical procedures, but we'll just use this equation. So this is the first order perturbation, and this is the second order perturbation. The structure is simple actually. And this one superscript indicates the order of lambda. So the original wave function here, and perturbation part. So this is basically like this: original wave function, then perturbation part, and then wave function. If it's one-dimensional problem, we do like this. And then second order problem, you see similar term is here, but n and k, they are different now, and k is summed up from any given values. Then on the numerator, en0 minus ek0. For the correction to the wave function, so zeroth order, and this is the first order term. So there could be second order term, third order term. You can calculate that, but it is rather complicated. So we'll stop here. First order perturbation is summed from lowest to the highest. So k0, zeroth order term, and then en0, ek0, Again, this is the first order. Yeah, I mean it is not squared here. It's just the first order on the in this side. Please note that we don't make the denominator to be 0, otherwise you have singularity, so we'll set this. So what does it mean? N and K, they are different. If N and K are different, their energy should be different. We need this condition, so this is something called non-degenerate. Degeneracy we learned, and it means that for different quantum numbers, energies are the same. Those indicate the degeneracy, but here we don't consider degeneracy, so it is called non-degenerate case. There could be degenerate case, but we'll skip the details of this, because our example in the end, I think that is the important part of this class. I want to let you know how we apply these theoretical mathematical terms into reality, the real research problem. So in the case we didn't consider degenerate case, so mathematics becomes even more complicated in this case, so we'll skip this part, and then we'll go into the complicated problem here. We want to make it simple and simple, but it is already complicated. Now we'll consider magnetic field. So this is actually a very short paper of mine in old days. So here we use the perturbation theory, and then we solve extremely difficult problem by using very simple perturbation. So basic idea here is, let's say we have certain quantum errors. Quantum errors are building blocks for the semiconductor industries. This sample, I remember, it's like gallium arsenide based samples. Well, it's something like indium gallium arsenide, barrier gallium arsenide. Gallium arsenide has the larger band gap, on the order of like 1.5 at very low temperature. This one slightly larger than 1 electron, but maybe like 1.2, something like that, on the order of. So this is smaller in energy, so it works as quantum well. This works as barrier. This is the basic idea of many of the semiconductor technology, quantum well and barrier. So we accumulate carriers within quantum well. Let's say quantum well size is L. It is defined like from minus L over 2 to L over 2. Then you have 3 different quantum state. But instead of quantum number equal to 1, quantum number equal to 2, quantum number equal to 3, my friend Fadier actually used different notation, like a ground state 0, first excited state, second excited state. Sometimes theorists prepare this representation because that's the way they indicate the ground state, and this ground state matches with our quantum number 1. Some theoretical paper use different representation. There are many theories in this simple paper actually. Did the measurement provide the intuitive picture, and theorists used their own representation and schemes. So please note that it is 0, 1, 2, but actually it is just the same with our quantum numbers 1, 2, 3. They match like this. Okay. Also remove this gallium arsenide part. We know the potential shape is symmetric here. So wave function will have certain parity. And let's say magnetic field is applied within the quantum layer along z-axis. Okay. And in undergraduate course of electromagnetism, you will learn something called vector potential. So another one of the most important or difficult problems in undergraduate studies. But you cannot calculate them all. So let's just accept for now. So this something called curl A, we call it curl. Probably you know that. Curl A. This is curl. And this A, vector potential, can be calculated like this. And when you consider wave functions, so wave function is changing along y-axis. Let's say potential axis is y. Again, this is the choice of my friend Fedier. And the xy plane is quantum L plane. If it looks quite complicated, still it's okay, right? You can just read through this paper. Then you can even learn more than any contents of those previous slides. You will learn more, I can guarantee you. So it is available from our, school. So please find it out. Just Google it out. Print it out, and quite easier than conventional other research papers, so you can read through it yourself. Anyway, there's a wave function along y-axis, and the others are just x and y plane part. You can easily see it is same with free carrier case. Right? And for the energy, so this is the y-directional part. But y-direction part should be influenced by quantum confinement. There must be quantum numbers. The others, just the same with free particle, free case carriers. And then here S is known as normalization factor, epsilon energy along y-axis, which is determined from Hamiltonian given by this one. Way too complicated, but still we don't have time, so let's just accept. So magnetic field is another very important parameter in research, and you will see this magnetic field application many times. So when you apply the magnetic field, you can just define, okay, let's say magnetic field is set to be z-axis, okay? Then you can just add these terms into the perturbation part. Okay? So others, this one is this potential shape, easy part, so H0. The others, complicated part, H prime, perturbation part. Then we apply this idea into perturbation theory. So energy is like En0, En1, En2, and others ignored. So we only go up to second order. So E1, e to the 1, e to the power. Okay. First order correction, let's call it first order correction, second order correction. It's already determined like this. So we put this H prime into here, H prime into here, so you can get it. And also the zeroth order, so wave function, this one, like this. So this is actually psi 1 zeroth order. But my friend Fedier said, call it like this. Yeah, CAD rotation with 0 number to indicate the ground state. Ground. Yeah, some people focus on this ground state, and this is first excited. First excited state, second excited state. So it's like this. Quantum number is 2. Quantum number is 3. And also these are not infinite barrier, but we will just simplify to be the same with infinite barrier problem to make it simple and to show what is going on in terms of perturbation theories. So these are the energies. You have calculated this energy so many times, right? And then we apply these ideas into this perturbation theory. So calculating the energy. Calculating the energy is not that difficult actually. Everybody can do that. It all based on the patience. Calculating wave function, everybody can do that, but it's a little bit more complicated. So we put this into here. Put this wave function into here. Wave functions. So H prime is given here. Wave function is given here. We put this, plug those informations into perturbation theory, then calculate the En. That's what we want to know. So yeah, from that part we will do the details in next class. So please find this paper and read through if you can. And you don't need to study all the way into details about perturbation theory. You don't need to do that. You just use this. You don't need to even remember. If it's necessary, you can just find the references. And then I'm pretty sure there will be a problem related with this, but the equation itself, the perturbation theory, will be provided. So you don't need to remember. You just practice how to use this perturbation theory. This paper will show you a good example.